Welcome to Calculus 1. I'm Dr. Jeff Groh. I'd like to begin by talking a little bit about functions and function notation, because a proper understanding of functions and function notation will underlie a lot of what we do. So first of all, I'd like to ask you, what is a function? Do you know what a function is? Do you know what anything is? I like to get at the issue that precise understandings of meanings of mathematical terms is important, and the failure to understand meanings properly leads to a lot of mathematical errors. Let me illustrate something. What is an item of furniture called a table? A lot of students come back at me, well, it's a flat surface with a certain number of legs. But what is a table really? Now, Merriam-Webster, I believe, gets this one wrong. They say it's a flat, smooth surface with supports, but that kind of is a after the fact looking back at the observable properties of a table. What do you mean by smooth and flat? How smooth is smooth? How flat is flat? How much variation is permitted? Could we have a table with pebbles on the top? I'm sure certainly we can. I've seen them. They're not exactly smooth, not exactly necessarily perfectly flat. In what sense is it a table if it doesn't satisfy Merriam-Webster's definition? No, Merriam-Webster got this one wrong. A table is a tool, and tools should not be defined by their observable properties, but by their use. Would a table still be a table if it were flush with the ceiling and you couldn't put anything on it? I say, no, it's not serving the function of a table at that point. It's serving more the function of a pillar. A table is a freestanding item of furniture, besides which one may sit, and upon which one may place items for ease of manipulation or for display. That, I think, accurately describes the function of a table. You put things on it for ease of manipulation or to display things. If you have to stand next to it, it's not a table. It's a counter. The precise meanings of words are so important in mathematics because the core value of the mathematician is truth. We need to deduce the absolute truth of the propositions that we make. This goes back to the ancient Greeks, to the mathematician, we actually know his name, Thales or Thales of Miletus. In our culture, people learn words intuitively, usually conversationally. They don't know necessarily precise meanings of the words, only how those words are functionally used. This almost explains the entire difficulty that people have with mathematics. In mathematics, if you use intuitive understandings of mathematical terms, you almost always end up in a ditch of error. So, save yourself a lot of grief. Learn the precise meanings of mathematical terms. We're going to be doing three main things. We're going to be conceptualizing, and that involves understanding the precise meanings of these terms that we're going to introduce. Second, we're going to be functionalizing those things and proceduralizing things. Then, we're going to need you to memorize certain facts. These are all handled by different areas of the brain. We're going to exercise all of those regions of the brain and not leave any of them undertrained. So, conceptualization, proceduralization, and memorization. Make sure you take heed of all three of those. There was an Italian woman, 40 years old, who had encephalitis. Encephalitis is a kind of inflammation in the brain. And as a consequence of this disease, she had permanent brain damage. It permanently damaged her lateral temporal lobes. As a consequence, she retained the ability to multiply three-digit numbers, to carry out exponents. She had a lot of mathematical algorithms proceduralized. Those procedures she could execute, but she didn't know what any of it meant. She lost any ability to understand the meaning of what she was doing. She could just do it. This illustrates that meaning and procedure are stored in different locations in the human brain. You can have an understanding of something and not be able to proceduralize it. Or you can proceduralize something and have no idea what it is or what it means. It's tragic either way. I want you to train both parts of your brain, both the meaning part and that procedural part. In addition, there was a man in San Diego, California, who had encephalitis. His brain was damaged in a different region, in the hippocampus. He lost the ability to form new memories. Over the course of 10 years, he met 200 times with the same researchers who came to his apartment to visit with him. Each time they arrived at his doorstep, it was a new introduction. He had no idea who they were. You can see then that this man had the ability to process meaning, the ability to proceduralize, to do things, but he could not form new memories. How devastating would that be? No. You need to exercise your hippocampus. There are certain things you need to memorize. In fact, sometimes if I'm writing a computer program, I'll execute a certain subroutine numerous times. If I'm going to use a particular computation multiple times in the same subroutine, it's better to store the outcome in memory and then just reuse that memorized value over and over again in the subroutine than it is to execute the computation over and over again, reproducing that value each time. You save a lot of time. Sometimes that savings can be important. There was a problem with the space shuttle engines. Someone had written the subroutine inefficiently, and it wasn't pointing the nozzles of the rockets exactly at the right place at the right time. They had to go back and rewrite that subroutine more efficiently, utilizing memory instead of algorithm, in order to point those rocket engines at the right place at the right time. The use of memory greatly facilitates the speed of computations. You have to memorize certain things. We're going to work on memory, procedure, and conceptualization, and also your rational deductive facilities as well during this course. I'd like to begin with the definition of function. First, an intuitive idea of what a function is. Intuition is entirely inadequate. But it's good to have some anyway. A function is like a meat grinder. Stuff goes in, goes round and round inside, and gets plopped out in another form. It's nice to know that functions have this kind of procedural idea representing them, but that is not the definition of function. Since a function is a type of relation, I'm first going to define what I mean by relation. A relation is a set of ordered pairs. We can graph sets of ordered pairs. Let me give you an example. If I draw this, that's just a collection of points in the plane. That is a set of ordered pairs. This would be the graph of a relation. If I write something like this and fill it in, making it all solid, all of the points inside of this ellipse, they're just a collection of points in the plane. That is a relation. To understand functions, let's go back to our meat grinder model. We'd like functions to be so that when I plug, say, peaches in, I get only ground peaches out. I don't get both ground peaches and ground plums out when I plug peaches into the input slot. I don't want to get two things out for a function. That wasn't true for relations. What does it mean to get only one output out? It means that for the graph of a function, for each x input, you can only get one y output, not two or more. You can get more than one y output for a relation. So how do we formalize this into a definition? A function, which I'll denote by a fancy cursive capital F, is a relation. So a function is a collection of ordered pairs. It just has to satisfy that vertical line test. Such that if xy1 and xy2 are elements of that relation, so if you have 2 points with potentially distinct y values, the y values in fact must be the same. They can't be different. This is the vertical line test written down in kind of a concrete form. So, is this the graph of a function? Yes. Is this the graph of a function? Oops. Doesn't satisfy the vertical line test. There is an x value that produces more than one y value, so this is not the graph of a function. It is a relation, but not a function. There's a certain notation that applies to functions. Let f be a function and suppose the point xy is an element of that collection of points. We write y equals f of x. By this notation, we have these parentheses which kind of represent the mouth of the function. That's the input slot. X is going in. The function f is eating that and doing stuff to it, and then it's plopping the y coordinate out. So this notation merely means that this point is an element of the function capital fancy F. I'd like to caution you about this notation. The parenthesis notation, where we have two variables juxtaposed, separated by parentheses, is sometimes referring to multiplication, but that is not what is being implied here. In other words, we have one notation, but two distinct interpretations based on the context. In the context of functions, we don't mean multiplication. We mean function evaluation. How can we have one notation with two distinct meanings? I have to say all mathematical notation is conventional. What do I mean by that? A convention is a piece of knowledge that is dependent upon an arbitrary choice. Arbitrary choices? Mathematical conventions exist. They're an important part of mathematics. All notation is conventional. It's based on an arbitrary choice. Since so much of mathematics depends upon arbitrary choices, that implies something important, that it is not possible to logically deduce a lot of mathematics. That's because it's based upon these arbitrary choices. Now, let me explain how it is that these arbitrary choices are legitimate and also necessary. I want you to think about different items of clothing that are blue. There are different kinds of blue. You might have a blue shirt that's different from your denim blue pants. How is it that there are different shades of blue, and where's the cutoff between blue and, say, purple? The color of light depends upon the wavelength of some light ray. Since the light wavelengths can be any number within a continuum, there are infinitely many different colors of light. However, we only have a finite number of color names since our language is finite. Consequently, we have to make some arbitrary boundaries between the color names in the light spectrum. Where those boundaries occur is by arbitrary choice. Once we've made that choice, it's then possible to communicate with each other what we mean by blue or purple by agreed convention. Those conventions may change over time and over cultures, but at least those people living within those cultures at that time will be able to convey to each other some notion of what it is that is blue. So in mathematics, we have a large number of conventions. In addition, sometimes we have one notation and distinct meanings. You have to interpret the meaning based on the context. Now, let's give it an example. Suppose my function is the function, say, 3x squared minus 4. The way that we interpret the parentheses notation is, if I want to shove in a number, let's say 2, this sequence of symbols represents an algorithm. It says it wants you to square the 2 and then multiply by 3 and then subtract 4. It gives you an algorithm to follow to find the output y for the input x. 2 squared is 4 times 3 is 12. 12 minus 4 is 8. Now let me ask you, what is f of squiggle? F of squiggle, this tells you exactly what to do with whatever goes in. It's 3 times squiggle squared minus 4. What is f of happy face? You got it. It's 3 times happy face squared minus 4. Now, where students usually screw up, and this is important, so listen up. What is f of x plus h? Remember, 3x squared minus 4 is an algorithm. It tells you what to do to the things that go into the function f. In this case, x plus h is going in. So what comes out is 3 times x plus h squared minus 4. I want you to focus on this until you get it right. A typical exam type problem for exam 1 would be to simplify f of x plus h minus f of x divided by h. You need to know how to do this. On this problem, it's going to be 3 times x plus h squared minus 4 minus the quantity 3x squared minus 4 all over h. Now, if you leave off the parentheses in this spot, you will get it wrong, and I will mark you off for violating the order of operations agreement. We're subtracting this entire expression, not just the first term. From here, we need to FOIL out this perfect square. That's 3 times the quantity x squared plus 2xh plus h squared minus 4 minus 3x squared minus 4 all over h. Still, do not forget the middle term. When you FOIL out the square of a binomial, you get this middle term, which is 2 times first times last. Can't tell you how many times my students forget that middle term, just because their algebraic skills are poor. Don't let that be you. Simplifying, when we distribute the 3 to each of the 3 terms inside of this first set of parentheses, we'll have a 3x squared. This term will exactly cancel the minus 3x squared over here. Notice that I'm numbering what cancels with what. The minus 4 cancels with the minus 4 over here. I find that labeling what cancels with what helps me read my notes later on. Distributing, we have 6xh plus 3h squared all over h. Now, I want you to be very careful. A lot of students would just cancel the h here, but you can't do that because you may not cancel from terms. A lot of students don't know the difference between a term and a factor. Factors are things that are multiplied on. Terms are things that are added together. The principle of cancellation is you may cancel a common factor from both the numerator and denominator. H on this term is a factor of the term, but it's not a factor of the entire numerator. To cancel, you have to reverse the distributive law and write this as h times the quantity, 6x plus 3h, all over h. Now h is a factor of the numerator and of the denominator. These problems are not over until you can cancel that h in the denominator. If you can't cancel the h in the denominator, you screwed up. The answer is 6x plus 3h. This is such an important process. I'd like to do another one with you. Suppose our function is the square root of 2x plus 3. Let's find and simplify f of x plus h minus f of x divided by h. This kind of expression is called a difference quotient. We're subtracting 2 different y values on the top. In the denominator, we have x plus h minus x, which reduces to just h. It too can be thought of as a difference between the x coordinates that we're plugging into the function in the numerator. On this particular problem, we have the square root. X plus h is going in for x. Whatever goes in for x gets multiplied by 2, has 3 added to that, and then the square root taken of all of that. Remember, this is an algorithm for what the function does to the things that go in. So this is going to be 2 times the quantity x plus h plus 3 minus the square root of 2x plus 3 divided by h. By the way, it's good form to put a downward flange at the end of your square roots. Students often write things so carelessly that they don't know themselves where that square root ends. I have an old calculator that was designed for engineers. On the square root button, it has that little downward flange. So I'm not just making this up. This is good engineering form. We need to communicate effectively. By the way, almost everything you write is being written for your future self. I've seen students write something so badly on one line that on the next line they misinterpret it and have a completely different interpretation, and the computation goes off to the rails at that point. They have failed in a matter of seconds to communicate to their future selves. Try to write things neatly and distinctly. Now, how do we simplify this expression? This involves a classic technique called rationalizing the numerator by multiplying top and bottom, numerator and denominator, by the conjugate. The conjugate is obtained by switching the sign in the middle between the two terms. In this case, we need to multiply top and bottom by the square root of the quantity x plus h plus 3 plus the square root of 2x plus 3 over the exact same thing. You have to multiply top and bottom by the same thing, or else it's not equal anymore. We're multiplying by something that is essentially 1. We'll maintain the value of the expression, but we'll just change the form. How this works is, you FOIL this out. When you FOIL this out, the square root on this first term cancels. You have 2 times the quantity, x plus h plus 3. When you multiply the outer terms, you get the opposite of what you get when you multiply the inner terms. And so all of that cancels out. We're left with the product of the last terms. The last terms will have a minus, and then the square root goes away, and we have 2x plus 3. Do not simplify the denominator, just leave it. Remember, this h has to cancel, or else we've screwed up. We'll have h times the square root of 2 times the quantity x plus h plus 3 plus the square root of 2x plus 3. Now, we get certain terms to cancel. The 3's will cancel. The 2x also cancels. What's left is 2h over h times the rest of the denominator, square root of 2 times x plus h plus 3 plus the square root of 2x plus 3. At this point, h is a common factor of both the numerator and the denominator, and so we can cancel that common factor. Our answer is 2 divided by the square root of 2 times the quantity x plus h plus 3 plus the square root of 2x plus 3. I want to do one more, just so we review your algebraic skills. Suppose our function is 1 over x. Let's calculate the difference quotient. f of x plus h minus f of x over h. What is f of x plus h in this case? Remember, x plus h is replacing x in the formula. So it's 1 over the quantity x plus h. From that we subtract f of x, which is 1 over x, all over h. At this point, you need to recognize that we are subtracting fractions. How do you subtract fractions? You have to have a common denominator. And so on the first term, I need to multiply by x over x. On the second term, I have to multiply by x plus h over x plus h. We're still all over h. Remember, when you divide fractions, you invert and multiply. Now, in the numerator, we have a common denominator. So when we subtract, the x's will cancel and we'll be left with minus h on the top. Inverting and multiplying will have 1 over h multiplied on the side. The h's cancel, and our answer is negative 1 over x times the quantity x plus h. Now, I want to give you a little preview of what is to come. There are two main problems in calculus: slope finding and area finding. It may not seem like these two processes are related. We will see that there is a deep connection later in the course. The slope formula that you learned way back in Algebra 1 is rise over run, difference in y values divided by the difference in x values. You might have even denoted the difference in the y values by delta y and the difference in x values by delta x. This is the capital letter delta. The lowercase letter delta looks like this. In our present context, suppose we have some function y equals f of x. Our goal is to try to find the slope of the tangent line. The tangent line just grazes the curve at this one point, like this. Suppose we're at some point A. We want to know the slope of the tangent line at A. The problem there is we can figure out the coordinates of this point, A, f of A. That only gives us 1 point. Our slope formula required that we have the coordinates of 2 points. So our basic idea will be to back off from this point to A plus h, and then we'll find the slope of the secant line. A line is called a secant line if it passes through 2 points on the curve. And the slope of the secant line is very easy because we have 2 points. You can see now why we're doing these difference quotients. These are slopes of secant lines. How can we leverage our knowledge of the slope of the secant lines to give us the slope of the tangent line? Well, the idea there is we have a gap of h units between A and A plus h. What we'll do is we'll take a limit. We'll have to understand limits to be able to do this, but we'll take a limit as this h gets smaller and smaller as h goes to 0. So the slope of the tangent line will be equal to the limit as h goes to 0 of the slope of the secant line. That's going to be the secret to finding the slope at that one point. Okay, so that's how we're going to resolve the slope of the tangent line problem. Believe it or not, the slope of the tangent line problem is related to a lot of problems in physics, chemistry, biology, all sciences. You would be amazed at the number of applications of this one simple little process. Now, our other problem. The other problem is area finding. So the idea goes like this. Suppose we have some function, and between points x equals a and x equals b, we would like to find the area of the undergraph. This too will involve a limiting process. We'll start by dividing the region up into little vertical strips. Then we'll approximate the areas of these vertical strips using little rectangles. If we add up the area of the rectangles, we get an approximation to the area of what is called the undergraph. But that's only an approximation. As you can see, if we used only 2 rectangles, we would get a much worse result. A lot more error with fewer rectangles. The key to this process is to take the limit as the number of rectangles goes to infinity, provided all of the rectangles get smaller. In that case, we can find the exact area of the undergraph, but it does require a limit. Both slope finding and area finding will require that we understand limits. So our first task will be to understand limits. To get an idea of how we should define limits, we should look at some examples. So the basic idea for limits is, if you have a nice smooth curve, as x gets closer and closer to a from each side, the y values will get closer and closer to some value L. Now, that value L might not be the function value, as you'll see in the next example. Suppose the graph has a little hole at A, and the function value has been displaced. So f of A is up here. The hole might occur at some value L. As we approach from each side the x value x equals A, the y values do not approach the function value, they approach the value L. In other words, however we define our notion of limit, we need to specifically ignore what happens at x equals A and only focus on what happens near x equals A. I want to look at another example. Suppose our function is sine of x divided by x. I want to consider what happens in the limit as x goes to 0 for this function, sine of x divided by x. And no, you cannot cancel the x and get an answer of sin. That doesn't work. Besides that, x in the numerator is not a factor of the numerator. Sine is not multiplied onto x. Sine is a function acting on x. It's doing horrible things to that x when it goes in. You don't even want to know until most of the way through calculus 2. But sine is a function, not a factor, so you may not cancel the x. What you can try, though, is get an idea of what this function does in the limit as x goes to 0 by plugging numbers in, x values that are close to 0, but not equal to 0. If you plug x equals 0 in, sine of 0 is 0. The sine function looks like this. As you approach 0, you get 0. If I plug in x equals 0 in the denominator, I'll have 0 divided by 0, which is undefined. However, I want you to beware. 0 divided by 0 in the context of limits means more work. It doesn't mean undefined. It means more work, because we don't care what happens at x equals 0. We want to know what happens near x equals 0. So I'm going to plug points into this function that are near x equals 0 and see what happens. Points like 0.1. We will need our calculators for this exercise, but make sure your calculator is in radian mode. Calculus, and especially limits, are done in radian mode. My calculator is giving me about 0.99833, etc. Let's try a number closer to 0 than just 1/10. How about 0.01? What is the value of this ratio as we squeeze way in there, 1/100th of a unit away from 0? My calculator is giving me 0.99998333334. So the number went from something close to 1 to something even closer to 1. What should the limit value be? Well, just to be sure, let's try something even closer. My calculator gives me 0.99, let's see, 1, 2, 3, 4, 5, 6 nines, an 8, and then a bunch of 3s. We're getting closer and closer to 1 as the x value gets closer and closer to 0. This is true even if you put a negative in front of these. Go ahead and try it. If you put a negative in front of these, you get the exact same positive values. So whatever this function does, as you get closer and closer to 0, the function value gets closer and closer to 1. Though there is a hole in the graph there, that doesn't mean that the limit doesn't exist. The limit, as we shall prove later in the course, is exactly 1. So, a few important lessons to learn here. If you just plug 0 in, and you get 0 divided by 0, that means more work. I'd like to look at another example or two. I want to know, what is the limit as x goes to 1 of this function x squared minus 1 over x minus 1? Now, there are some subtle things that you can do here. The numerator does factor as a difference of squares. It factors as x minus 1 times x plus 1. And the denominator is still x minus 1. So we can kind of think of this as the limit as x goes to 1 of x minus 1 over x minus 1 times x plus 1. X minus 1 divided by x minus 1 is equal to 1 everywhere except at x equals 1. But we specifically need to ignore what happens at the x value that we're tending towards when we are considering limits. So this will be 1 everywhere that matters, everywhere except at x equals 1. The other factor, as x tends to 1, goes to 2. 2 times 1, the limit should be 2. We should also check this by maybe plotting some points, just for emphasis. If we're headed to 1, we need to choose values of x that are close to 1 but not equal to 1. How about 1.001? Is that close enough for you? My calculator gives me 2.001. And what about at 0.999? What is the limit there? Well, my calculator gives me 1.999. Very, very close to 2 on each side. So this function looks like it's headed towards a value of 2 as you approach 1 on each side in the domain. In the last example, we had to check out points on both sides of 1 to make sure that they were going to the same value. That is necessary is illustrated by the next example. Suppose I have f of x equals the absolute value of x minus 1 over x minus 1. This function has an interesting graph. It's not continuous at 1. At x equals 1, we get 0 divided by 0, which is undefined. What happens to this function when x is bigger than 1? If x is bigger than 1, then x minus 1 is positive, and then the absolute value does nothing. The absolute value does nothing to positive numbers that go in. It just spits them out the same. So if I have a number divided by itself, I should get a height of 1. And that's true for any x value that I plug in bigger than 1. Now, what happens when I plug in values smaller than 1? If x is smaller than 1, say 0, the top will give me the absolute value of negative 1, which is positive 1. The bottom will be negative 1. 1 divided by negative 1 is negative 1. If I have a number with the same magnitude but opposite signs, the ratio will always be minus 1. Everywhere to the left of x equals 1, the height is negative 1. So, what happens in the limit as we approach 1? Well, if we approach from the right, we should get a height of 1, but if we approach from the left, we get a height of negative 1. In this case, the limit as x tends to 1 of the absolute value of x minus 1 over x minus 1 does not exist. Because we did not approach one particular value as we approached 1 from both the right and the left. From the right, the y values were 1, and on the left, the y values were minus 1, not the same value. To illustrate another thing that can happen, let's consider the limit as x goes to 0 of the sine of 1 over x. We'll start by having you graph the sine of 1 over x. What does that thing look like? You need to be careful. The calculator needs to be in radian mode. The window should be fairly narrow between negative 0.1 for the x and positive 0.1 for the x. Sine is a bounded function going between negative 1 and 1. So make your minimum y minus 1 and your maximum y positive 1. The minimum x negative 0.1, the maximum x positive 0.1. Now, if you've done this correctly, you should get something like this. The curve oscillates an infinite number of times as you get closer and closer to 0. And it does this on both sides. It goes up and down an infinite number of times as you get closer and closer to the origin. The function value keeps oscillating back and forth. There's so much oscillation. Ask yourself, does the function value settle on any one y value in the limit? It doesn't seem so. It's oscillating back and forth. It has so much oscillation. The limit does not exist. It doesn't settle down on any one value. We can change this last example just a little bit, and it changes the outcome entirely. Graph this function now, multiply by x. That changes the amplitude. You now have a variable amplitude. The amplitude varies between the curves y equals x and y equals negative x. The curve will oscillate between these two an infinite number of times. Does the function settle on any one y value as you get in close to 0? All of those amplitudes are squished down. The function must tend to a limit of 0 as x goes to 0. So you see, the infinite oscillation wasn't necessarily the problem. Without this squishing amplitude, we get nothing, but when we squish that amplitude down to 0, we force the function to go to a y value of 0 as x tends to 0. Again, if you just plug x equals 0 in, 1 over 0 is undefined. Just because a function is undefined at one particular point doesn't mean that the limit does not exist. The limit in this case is 0. We have not yet stated a formal definition of what we mean by limit. We're trying to build up to that. We've given some examples of what we might be looking for. We want to specifically ignore what happens at the x value that we're tending towards, and only concern ourselves with what happens as we approach from both sides. We'll continue this discussion in our next lecture.